So I'm Ben, for those who don't know me. I'm a postdoc at University of Tokyo, working kind of at the intersection of large-scale structure, machine learning, and hydrodynamical simulations. So I kind of work in maybe a slightly different regime usually than what a lot of people have heard talking about, where I'm kind of quite interested in the cosmic web, the small-scale structure, really peering down to the 1 megaparsec type scale, the sub-megaparsec type scale, which motivates kind of a new way to look at the idea of field-level inference, a new way to look at forward models for this kind of regime. So one of the main motivations for this is my work with PFS Galaxy Evolution Survey. So people are probably familiar with PFS Cosmology Survey. There have been a couple of mentions of it so far. The Galaxy Evolution Survey is kind of the other, there's 3 wedges, the PFS pie. So there's the Cosmology, Galaxy Evolution, and Galactic Archaeology. And so I'm the chair of the large-scale structure working group within the Galaxy Evolution Survey. And so that really tries to track the formation evolution of galaxies throughout cosmic time. So going from high redshift at redshift 6/7, looking at Lyman alpha emitters there, all the way down to redshift 2, which I used to call high redshift back in the day, but now it's pretty low redshift. And then further down to the low Z sample. And so at redshift 2 to 3, we're really interested in the star formation history, formation of large-scale structure, and how that corresponds to this peak of star formation we see, cosmic noon, at redshift 2. And we track it through various ways, like Lyman alpha forest tomography. But since I'm at this workshop, we're interested in a field-level approach, right? We really want to dive in and see how do we try to model these things at the field level. I was told I get an extra 5 minutes of time with including the meme. So a lot of ways I work on this has been in the past with various surrogate modeling to do the forward modeling. So you run a particle mesh simulation, run an n-body simulation, and paint on your Lyman alpha forest signal various ways. So with various machine learning techniques. Most recently, we've been working with Carol on a stochastic interpolate model. But I'm not going to talk about this today, but if people are interested, feel free to ask me later. We'll be talking about kind of attacking the problem head on, trying to use hydrodynamical simulations and actually make the hydrodynamical simulations themselves differentiable. That way you can solve inverse problems, you can backpropagate through the hydrodynamics to kind of do what everybody's doing with particle mesh and bias models, but with the actual hydrodynamics. That involves coding up the Euler equations on a grid using a Eulerian scheme. So here's just a kind of a little toy example showing no gravity, constant medium. This is based on some old 4chan code I found, because I never did anything really directly with hydrodynamical simulations before this, so it was kind of a fun learning experience. But there's a lot of great benefits that come when you start taking these equations, coding them up on JAX, putting them on GPU. Things get crazy fast in this kind of regime. Operations vectorize quite nicely, and you can then use a lot of the JAX tricks and auto differentiation tricks to make this whole thing end-to-end differentiable. So you can, once you have a differentiable hydrosim, you can try to solve inverse problems, make pretty pictures. So here's kind of a little toy example, just with that earlier picture of the 3 blast waves. You can try to inverse solve to find the best fit predicted field. In this case, from like a Bayesian standpoint, it's pretty unlikely you'll get 3 isolated points. So the prior effects are significant, but you could then go further and make even prettier pictures. So here's an example, making a nice hydrosim parallelized across GPU to make diff hydro. Usually I give these talks at Asian institutions, like in Taiwan and Japan, and then I get the kanji from each of those places, the characters, and inverse solve those, and that's usually a little bit prettier than this, but I cannot find a good kanji for Vienna. So then we can go further and do this cosmologically. So try to couple it to dark matter. And so this is using the JAX PM that we've heard about in passing, I think in a few talks now. So that means jointly evolving the gas density, gas temperature, as well as the dark matter on a grid. So, and you can see that your large-scale structure forms, and you get the thermal pressure support in the gas. And so we can now do the same kinds of tricks and try to inverse solve for some kind of fake mock data. So here's just a really basic example. You have some kind of noisy image of a cluster in some kind of thermal like signal. This could be like a TSZ or X-ray like surrogate. And I'm just going to evolve a small box and try to find the best fit. And so we can now do that, and we with a simple optimization method. You could also use sampling or something like that, but just for illustrative purpose, using optimization. And really within just a few samples, using the derivative information, you can really reconstruct the initial conditions that give rise to this cluster. Now, the last component of a normal hydrosim, at least the ones people frequently use, are subgrid models, because we are also interested in the stars. And when you're looking at, say, redshift 2, redshift 3, people are quite interested in the effects of feedback on the gas. So if there's AGN or supernova feedback, how does that affect the thermal state of the gas? How does that affect the Lyman alpha forest signals that you might get from this regime? And so the goal here is to make this differentiable in the end. And so we take a pretty simple model. This is inspired by kind of what illustrious TNG does. Basically, if you have cold, dense gas, there's some probability you form stars in that region. Here, once we form a star, we track it like the dark matter particles and let it inject energy into the gas, the surrounding gas. So this can be made differentiable with this Gumbel softmax trick. People are interested in kind of using the same trick for HOD models. You can ask me or Francois, who's also involved. We can now run crazy hydrosims. It's really fun to make things blow up, as you could tell by my earlier examples. So here's a example where I just turned the subgrid physics up to 11, just to show that you can blow up the universe if you really wanted to. You could also run the same kind of thing with a more realistic model. So here is, I think it was the same initial conditions earlier on, but now we're also including star formation. You can see the star field over here as the simulation progresses. And we're letting these stars inject energy. And so again, at this point, it's all completely physics. We're just solving equations. We're not training neural networks or anything like that, but still we're able to make this all differentiable and backpropagate through. So yeah, just kind of showing this toy model. We didn't yet, carefully compare it against other simulations, just as an example. But you can see as we increase energy, the injection scale, or increase the critical density you need for star formation, you get lots of different kind of realistic-looking like feedback properties. And so then you can go and try to do inference, including these properties. So for just to avoid the whole issue of sampling initial conditions and initial phases at once, we're just looking at power spectra estimates. And so we could do this at the power spectra level. We have a differentiable code to calculate the power spectra from these fields. You can see that you can take derivatives with respect to cosmological parameters as well as astrophysical parameters, and you can match up the results you get from a finite difference type scheme. Yeah. What this is, so this is just only stellar feedback at this point. You could, it's such a toy model, you could kind of just call it whatever you want. You could call it AGN, you could call it any of these things. Yeah. The issue with AGN and how it's normally modeled is you have to track black hole particles as well. But you could imagine you could include those as particles evolving gravitationally and have their mass change over time as well, but I've not yet coded that up. So then we can do HMC type analyses, derivative-based analyses in both cosmological parameter space as well as astrophysical parameter space to do this joint inference. So this is all very cool, but in the end, particularly if you are interested in really large volumes, hydrodynamical simulations are still pretty expensive. Even if you get it all on GPU, even if you have a lot of GPUs, running these simulations, particularly in this fixed grid type of regime, at the resolution you would need for real inference would be quite expensive. And this was just a kind of relatively expensive run with diffhydro on this Kelvin-Helmholtz instability, which took still a couple seconds to run. But then if you really want to solve it in, quote, the real way by astrophysical standards with things like AMR, it's much more expensive. Sorry. You can see here, when you involve AMR, you really try to solve things across a wide range of scales. It's quite, you get really qualitatively different structures, even with the same initial conditions. And so we really want to be able to capture this multi-scale effects within our differentiable hydrodynamics, possibly, hopefully, without having to actually resolve all these scales and resolve the physics of all these scales. This simulation here took, I think, a day to run on NERSC. I was playing around with it with the this Athena benchmark code, while my diffhydro here took, a couple seconds. So it'd be great to be able to capture this type of physics still without enormously increasing computational cost. So that motivates my this solver and loop approach. So the idea is to figure out a way to essentially map between low resolution, high resolution simulations, but not at late time, but all throughout the course of the evolution. So to actually correct every time step how we're doing our evolution to include this, this small scale physics effect. So in this case, you could kind of set this up lots of different ways. Here I'm kind of showing low resolution, high resolution in terms of pixel resolution. You can imagine this could also be, whether you're doing adaptive mesh refinement, what type of Riemann solver you're using for your fluid mechanics, whether or not you want to really do things really large time steps beyond what normal convergence criteria would suggest, or what I think kind of most excitingly, and I'll get back to at the end of the talk, is actually including kind of expensive subgrid physics or possibly unknown subgrid physics as this kind of unknown that we want to solve. So to kind of show this graphically, in the kind of case of you have a benchmark simulation that's really expensive, you have my cheap diff hydro code, you want my cheap hydro code to match the high resolution simulation, you can kind of set up a correction network. So you call this f theta with some neural network parameters theta. And then what you do is you run your normal simulation in the standard way. So you can just give me whatever simulation you want with the standard time steps. I take that same initial condition, run it through my code, but then every single time step I perform this correction. And so you could perform this correction to either the state vector or the calculated flux, lots of different options depending on what you're interested in. But then the key is every single time step you apply this correction. And then when you backpropagate through to figure out what your neural network parameters are, you have to backpropagate through every single time step. You have to backpropagate through every time you apply this network. Hopefully, if you really want to make this flexible, you make this network not depend on the time. So it only depends on the current state. And then you want to minimize this overall loss. So to kind of show that in maybe a different way, you can imagine you have a solution space manifold here where your trajectory as time evolves is this dotted line. You can imagine you run your high resolution simulation, which is trying to capture the underlying true physics, hopefully, which is this red line. And if you just run a normal low resolution simulation, you could imagine it will end up diverging at late times. And so what we want to do is we want to learn a correction network, which is essentially a vector field on this manifold that basically pushes you towards the correct solution. So at every time step, you're getting pushed hopefully closer and closer. So your end trajectory is more like this line here. And hopefully you end up closer to the underlying truth if you train the network correctly. And in our case, we're going to use that Kelvin-Helmholtz instability example with roughly 1,000 time steps. So it's quite a thorough analysis here. We're not like just doing 10 time steps or something like that. We want to map from our adaptive mesh refinement example. So we're trying to map from our uncorrected or static mesh low resolution example to our adaptive mesh refinement example. And we use a pretty simple correction network here. So it's, I literally just kind of threw together a bunch of layers and a bunch of activation functions. I did like zero optimization. I think I tried one layer, it didn't work. I just put a bunch together and it worked. But the key is at the end, it's fully convolutional. So that means you can train it on relatively small boxes and apply it to big boxes, as well as it has relatively few parameters. So you're less likely to encounter kind of overtraining issues. And so I spent a lot of time staring at these beautiful swirls to try and think about how the model's performing. So you can kind of look here at this as we kind of trained it up to time step 1 and then ran it further to time step 2, so twice the physical time. And you can see the uncorrected network over here, the correction here, and the full AMR over here. So you can stare at all the squiggles, like I spent too much time staring at squiggles. And you can see that with this correction network trained, you can actually capture qualitatively different phenomenon. So for example, here in the uncorrected example, you're not resolving this kind of double swirl pattern. You kind of get this one single arc. And here you're actually resolving the double swirl. Here you get no swirl, and here you're getting the swirls. So this is clearly learning something qualitatively different at a really computationally inexpensive cost. It essentially costs no additional time, very marginal, sub% level additional time to run it with this correction network versus just the standard solver. And then you can look at it quantitatively, look at pixel error, for example. You get significantly less pixel error even when you forward predict past where it's trained on. Now you can look at summary statistics like cross correlation coefficients. things like that. People have ideas of good ways to quantify how pretty the swirls are. Beyond this, I'm all ears. And so now the kind of goal in the future, or the goal that we're currently working on, is trying to encode the same approach, but to some kind of cosmological astrophysical system. So this is with an undergrad student at Princeton, Lily, who was working with me over the summer. And the goal is to do the same type of approach, but for the star formation physics. So in this case, we're taking a step back and just doing only particle mesh simulations, not doing the full hydro. But the idea is that we take initial conditions. This is from the CAMEL simulation set. We take the stellar mass field at late times, so at redshift 2 and redshift 0. And the goal is to evolve the initial conditions with a particle mesh simulation, solve at every time step for a stellar formation field, create those star particles. In this case, we're just going to paint them onto the dark matter particles, just to make as a test example, and see if we can train this the same kind of subgrid physics solver and loop method. And it seems to work quite well at the pretty picture level. So here we have at redshift 2 our CAMEL's reference simulation here. This is all this stellar mass field. Here we're at much more coarse resolution, but we still get qualitatively the same structures. And going forward to redshift 0, we still can recover the same structures. And then going into looking at more quantitatively at the power spectral level across correlation coefficient level, we still get quite good performance. And I think pretty much the main limitation here is just the particle mesh simulation, the relatively coarse resolution, and the coarse gravity solving. I think that's probably the dominant error term that's contributing to the fact that we're not getting up to much smaller scales here. And so we're currently investigating this more, checking on how much this model would generalize. We trained on one CAMEL simulation. The hope is that it can work on every other CAMEL simulation. You could also encode, make this type of model conditional on the astrophysical parameters. So CAMEL's simulation set, they span a wide range of supernova feedback. You could also check how much it generalizes. Yeah, as I said, you can check how much how we can explain this type of model. It's a relatively simple CNN. You can do various response type analyses to figure out what features it's picking up on. And what I think is most exciting about this kind of approach is, in this case, we're training it on the simulations themselves, but you could imagine you could use the same model and train it on the data, right? So you have a light cone of galaxies of star field formation physics that you're observing. And the idea is that we could actually jointly solve for initial conditions, as well as with this kind of relatively lightweight neural network that can describe the actual formation of the galaxies. So that's kind of what we're hoping to do in the future. So to summarize here, hopefully I convinced you that we can make hydrodynamical simulations to make beautiful images and pretty pictures, but also hopefully soon we'll be using them to actually do cosmological constraints as well as astrophysical constraints, and that these kinds of solver and loop approaches are a really kind of novel thing you can do with the setup, right? It's not just doing field level inference in the traditional sense, but you can use these differentiable models to speed up traditional simulations. You can use this as a tool, even if you don't believe in field level inference at all, even if you think this is a terrible idea to do explicit field level inference, you can still say, oh, well, this is a way to really quickly generate new hydrosims at in a relatively robust way without the same computational cost. Thanks.